So let me remind you that the midterm exam 1 is a week from today, which is Monday, March 11, on campus in Gillette from 9 o'clock to 10:40 a.m. in person. Must be there. And it's a normal exam, closed book, no notes, and so forth. And the exam covers chapters 1 to 5 in Journey Through Genius by William Dunn. And as I've said on numerous occasions, you are expected to know everything in the book. Right? That's the simplest thing. Though a good review includes the homeworks and certainly the great theorems in each of the chapters. Any questions about any of this? So I have improved, but I'm going to do that today, Heron's formula. So Heron's formula for the area of a triangle, if you have a triangle with sides A, B, and C, the perimeter is A plus B plus C, and half the perimeter, which we call the semi-perimeter S, this is the semi-perimeter. So if you know the three sides of the triangle, you can certainly add them up and divide by 2. And the formula says that the area, which the book is denoting by K, is the square root of S times S minus A, S minus B, S minus C. So this is Heron's formula. And we did go over, I think, last week, some of the preliminary results in Heron's formula. These are some results in geometry, and I'll review them right now. But this is the formula. And, if you take a triangle, 7, 11, 14, right? What's the area of the triangle? You can say it's half the base times the height, but you don't know the height. You just know 7, 11, and 14. So the semi-perimeter is 7 plus 11 plus 14 over 2. Let's see, 7 plus 11 is 18. 18 plus 14 is 32 over 2. The semi-perimeter is 16. So the area, K, is the square root of 16 times 16 minus 7, 16 minus 11, 16 minus 14. That's the square root of 16 times 9 times 5 times 2. That's what it is. Because the square root of 16 is 4, the square root of, this is a 2, square root of 9 is 3, So this is 12 times the square root of 10. That's the area of the triangle. In fact, once you know the area of the triangle, you can find the height, because the height, the area is also 1/2 the height times the base. So 7h. So if you wanted to, you could solve for h. H is equal to 12 root 10 over 7. And I think you would be hard pressed to find that any other way. Okay, any questions about this? So you do have to know Heron's formula, right? If I give you a triangle and ask you to find the area, and you're not given the height, you're only given the 3 sides, then Heron's formula gives you the area. So there's some preliminary results we're going to use. The first proposition says that if you have any triangle and you bisect the angles, the angle bisectors meet at a point which is the center of the triangle's inscribed circle. So the unique circle that can be inscribed in a triangle is the point where the angle bisectors meet. So in words, this is the bisectors of the angles of a triangle meet at a point. This is the point where they meet. That is the center of the inscribed circle of the triangle. And that point is sometimes called the incenter, which is not important, just that this point has a name. And it's not hard to prove this, but I'm not going to prove this yet. The second proposition says, if you have a right triangle, and I'll draw it with the hypotenuse as the base, so this is a right triangle. If a perpendicular is drawn from the right angle to the base, the triangles on each side of it are similar to the whole triangle and to each other. So if this is, for example, A, B, and C, and this point is D, then triangle ABC, that's the big triangle, triangle DAB, and triangle DCA are similar. Similar triangles means they have the same angles. That's proposition 2. Proposition 3 says that if you have a right triangle, I'll draw it like this now. This is a right triangle, ABC, and you take the midpoint of the hypotenuse, call that M. This is equidistant from the 3 vertices. Of course, so the midpoint of the hypotenuse of a right triangle is equidistant to the three vertices. Now, of course, if M is the midpoint of BC, M is equidistant to B and C, but also if you take the line from A to M or from M to A, that has to be the same length. So the distance from A to M is the distance from B to M is the distance from C to M, right? That's what this says. The midpoint of the hypotenuse of a right triangle is equidistant to the three vertices. Proposition 4 says that if you have an equilateral triangle, sorry, not equal, if you have a quadrilateral, this is a quadrilateral, and
Professor, can you put the paper up a little? Thank you.
Sure. It's also good if you have the book, because on this proof, I'm trying to follow the book very carefully. So, and I try to make the drawings labeled the same way as in the text. But here we have a quadrilateral. It's a four-sided figure. And AB are one pair of opposite vertices, and OH are another pair of opposite vertices. And the proposition says, if you have, let me draw this line. So this is a diagonal from A to B. So we have the angle HAB. If angle HAB, and I draw the other diagonal. If angle HAB and angle HOB are right angles. Sorry. Yeah, that's right. If these are right angles, so if it turns out that these are right angles, then you can inscribe a circle around the quadrilateral. So then a circle can be drawn passing through the four vertices A, O, B, and H. So if these angles are right angles, then in fact, there's a circle that can be drawn passing through the vertices of the quadrilateral. So the quadrilateral is what is called a cyclic quadrilateral. And the last proposition, Prop 5, says the opposite angles of a cyclic quadrilateral sum to two right angles. So if you have a circle, oops, yuck. circle with the compass. So a cyclic quadrilateral is a quadrilateral that can be inscribed in a circle. If you take a pair of opposite angles, I mean, that adds up to two right angles. So this plus this is two right angles. This plus this is two right angles. Remember, if you have any quadrilateral, like a square or a rectangle, or the most symmetric cases, the sum of the four interior angles is four right angles. And if you have a cyclic quadrilateral, the sum of every opposite pair of angles is two right angles.
Professor,
Yeah,
I have a bit of a question
go
that
ahead.
I'm thinking about right now. So for Proposition 3, right, we have a midpoint between B and C, where B and C are equal in distance, right?
Well,
And
wait, not, I mean,
Hmm?
B and C are the same distance from M because M is the midpoint of the line BC.
yeah, the same distance. And we're also saying that
And there's
MA
also the same
is,
distance to A.
so I'm thinking, can we make a circle out of this where
Sure.
M is the radius?
Yeah, of course. Not, well, M is the center and BC, so and BM, CM, and AM would be radii. Absolutely.
Okay.
As you just draw the circle with center at M, with this is the radius, and it'll go through these 3 points because the circle is all, a circle with a given radius is all points to, with that distance. If the circle with radius R and center M is all points whose distance to M is R. So if this is R
Right.
and this is R and this is R, then the circle with radius R and center at M certainly goes through these 3 points.
Right.
That's also a special case or an instance of the fact that if you have any circle and any diameter and you take any point on the circumference, this inscribed angle is always a right angle.
Oh,
Right?
I hadn't realized.
Right. That's a very simple. I mean, that's something we showed earlier, I think.
Well, thank you, Professor.
Okay. Okay. So let's see whether I can prove Heron's formula. So we have a triangle ABC, and so proof of Heron's formula. So we have a triangle, and you can take a side which is not shorter than any of the other sides. You could have an equilateral triangle, all the sides are the same. An isosceles triangle, two sides are equal. But in any case, if you have any triangle, with three sides, just pick one side to be, which is the longest, and call that AB, and the third, or the vertices AB and the third C. So we have a triangle ABC, and we want to prove that the area K is the square root of S, S minus A, S minus B, S minus C. That's what we want to prove. So suppose we just let AB be the longest, or the easiest side of the triangle. That is, neither of the other two sides is strictly bigger than AB. Okay. So if you take the angle bisectors, they meet at a point which is the incenter of the circle. And there is, so this point is equidistant to the three sides. And you can inscribe a circle in the triangle, which is tangent to all three sides of the triangle. So this called the center of the inscribed circle O, and draw the perpendiculars to the three sides of the triangle and call these points D, E, and F. So OD, OE, and OF are radii. They have the same length, right? So we have the inscribed circle with center at O and radius, let's call it R, which is the distance from O to D, the distance from O to E, the distance from O to F. Now, if you look at triangle AOB, the base is AB and the height is OD. So let's call this distance little c. So the area of, and the height is the radius r. The area of triangle AOB is 1/2 the base times the height. Let's call the distance from A to C B, and the distance from B to C A. So the area of triangle AOB is half the height R times the base C. The area of triangle AOC is 1/2 the base B times the height R. And the area of triangle BOC is 1/2 the base, which is A, times the height R. So if you add up these three triangles, the total area K, I've taken the big triangle and divided it up into three smaller triangles, and these are their areas. So the area of the whole triangle is the sum of the areas of the three triangles. That's 1/2 AR plus 1/2 BR plus 1/2 CR. That's equal to, I can factor out the R, A plus B plus C over 2. A plus B plus C is the perimeter. A plus B plus C over 2 is half the perimeter, or the semi-perimeter, so that's equal to S. So the area of the triangle is R times S, where S is the semi-perimeter and R is the distance from the midpoint of the angle bisectors, or the distance from the center of the inscribed circle to the edges. Okay. Also, so this is part A. If you want to, if you're following in the text, this is part A. There are 3 parts. In part B, we have to look at our triangle again. So in this triangle, we have, let me sketch it again. This is the in-center. This is A, B, C. When I draw the perpendiculars to the sides, this is the radius of the inscribed circle. If I look at these 2 right triangles, let me call this, I called this F, and I called this D. If I made this perpendicular, this was what I called E. I can look at these 2 triangles, this triangle and this triangle. So these are 2 right triangles. They share the hypotenuse, they're the same, and this leg is the radius. So if you have 2 right triangles and 2 sides are the same lengths, the third sides are, and these are congruent triangles. So triangle AOD, that's the red triangle, is congruent to triangle AOF. These 2 triangles are congruent. And similarly, if I draw the line from O to B, this is a right angle, this is a right angle. They share the radii and the hypotenuse. These 2 triangles are going to be congruent. Triangle BOD is congruent to triangle BOE. And if I draw this line and look at these 2 right triangles, triangle COE, this guy, is congruent to triangle COF. So AD equals AF. Because AD and AF are corresponding sides of congruent triangles. BD equals BE. Because BD and BE are corresponding sides of congruent triangles. And CE has the same length as CF, because CE and CF are corresponding sides of congruent triangles. And similarly, the angles AOF and AOD, angle AOF, angle AOD, so angle AOF equals angle AOD, and angle COF and COE are equal. COE and COF. And angle BOD, this angle and this angle, angle BOD equals angle BOE. So whenever you have congruent triangles, the corresponding sides are equal and the corresponding angles are equal. And that's all we're saying. Okay. Now comes a more complicated picture. So let me again draw the picture that we have. We have this is A, B, C. This is the in-center. And we have the inscribed circle. So that's the circle with center 0 tangent to the three sides. The points where the circle touches the sides are D, E, and F. And these are right angles. And the first thing we do is extend the side AB to a point G where so we choose G, choose the point G on the line through A and B. So here's the line through A and B. And we're going to choose a point G such that, this is a G, such that the distance from A to G is the distance from C to E. So the distance from C to E is this. So we're going to pick a point G here so that the distance from A to G is the distance from C to E. Okay? So this is the first really strange thing that we're doing. Why in the world do that? Well, sometimes people have good ideas. So the distance from B to G is the sum of these three distances. The distance from B to D, plus the distance from A to D, plus the distance from A to G. But the distance from A to G is the distance from C to E. So this is the distance from B to D plus A to D, and I can replace the distance from A to G with the distance from C to E. Right, that's by construction. That's how we constructed by construction of the point G. Now, now we can do something weird. Remember that 1/2 times 2 is 1. So if you have any number x, that's 1/2 times 2x. So the distance from B to D is the same as 1/2 times 2 times the distance from B to D. And the distance from A to D is 1/2 times 2 times the distance from A to D. And the distance from C to E is 1/2 2 times the distance from C to E. So that's kind of trivial. Now, the distance from B to D equals the distance from B to E. So this is 1/2 BD plus BE, because these two distances are the same. And the distance from A to D is the distance from A to F. So 2 times the distance from A to D is like the distance from A to D plus the distance from A to F. And the distance from C to E is the distance from C to F. So this is the same as the distance from C to E plus the distance from C to F. And now if you look at this, you see a kind of a miracle occurring. The distance from AD plus the distance from B to D, that is this and this, that's just the distance from A to B. And the distance from A to D plus the distance, the distance from A to F plus the distance from C to F. Here's the distance from A to F, and here's the distance from C to F. That's just the distance from A to C. And the distance from B to E plus the distance from E to C is the same as the distance from B to C. If we call this distance A, that distance B, and this distance C, this is just a half, A plus B plus C. That's a half the perimeter, that's S. So the distance from B to G by a miracle or brilliant construction is the semi-perimeter, S. Now, remember in Heron's formula, we had 4 different quantities: S, S minus A, S minus B, and S minus C. So I just found a geometrical construction of S. S is the length from B to G. What about S minus A, S minus B, and S minus C? So S minus A, S is the length from B to G, and A is the length from B to C. So I subtract them. S minus A is this length minus this length. The length from B to G is, it's given right up there, BD plus AD plus AG minus BC, but BC is BE plus EC. And this is BD plus AD. The distance from A to G is the same by construction as the distance from C to E minus BE, which is the same as BD, plus the distance from C to E. So if you look at it, these cancel, and you're left with just the distance from A to D. So the distance from A to D, this, is equal to S minus A. Let's look at S minus C. S minus C is what? S is the length of BG.
Yes.
C,
Good. So, go
is
ahead.
there a question? So S is the distance from B to G. C is the distance from A to B. If you take the distance from B to G minus, sorry, C B to G minus the distance from A to B, right? So you take the distance from B to G minus the distance from B to A, you're left with the distance from A to G. So the length of this line from A to G is S minus B. And what would be lovely if the distance from B to D were equal to S minus C. Sorry, this is S minus C. That's what I just calculated. And what would be lovely if the distance from B to D were equal to S minus B. So let's just see if we can do that calculation right down here. S minus B is the distance, S is the distance from B to G, B is the distance from A to C. The distance BG is BD plus AD plus AG. This is all in the book, so if my writing is bad, just have to look at the book. Minus the distance from A to C, which is AF plus CF. But CF is the same as CE, so just make that CE. And AF is the same as AD. So AD and AD cancel. AG is the same as CE. So these cancel. And we're left with just BD. So the distance from B to D is S minus B. So now we have a really remarkable picture. I have this line from B to G. The length is equal to S, the semi-perimeter. But that line is divided into three pieces whose sides are exactly the three quantities that go into Heron's formula, S minus A, S minus B, and S minus C. So the last part of the proof is to somehow put this together and prove Heron's formula. So let me redraw this picture and add one more line. So I have the line from G to A to D to B, and my triangle is this, ABC. And I had the incenter, O, and the perpendiculars to the sides, D, E, and F. That's what I have. So now what we do is we have the line OB. And perpendicular to that I draw a line from B. And we have the line through B, A, and G, and perpendicular to that, I draw a line like this. So this line is drawn perpendicular to BC. This line is drawn perpendicular to AB. And these lines intersect at some point H. And there's one more point I want, which is we draw the line from O to H. So I have this line perpendicular to OB. I have this line perpendicular to AB. And then I want to draw the line from B to H. Well, wait, something isn't quite right. Okay. Let me draw this picture again. Let me do it better. So this is my triangle A, B, C. This is the incenter O. And I have the perpendiculars to the three sides of the triangle. And these points are D, E, and F. And then I extended AB to a point G, where the distance from A to G equal the distance from C to E. Okay. And I also look at each of the angle bisectors from the incenter to the three vertices of the triangle. So on the line GAB, I construct a perpendicular. And on the line OB, we draw a line OL perpendicular to OB. So I want to draw that so the right angle is here. So this is a right angle. I draw that. And these two perpendicular lines meet, and this is the point H. And then I want to draw one more line, which is the line from B to H. So it's really hard to figure out what's going on here without just staring and staring and staring a lot. But I now have a quadrilateral. I have a lot of quadrilaterals, but the quadrilateral I want to look at is AHBO. Let me, so I have from A to H, H to B, B to O, and O back to A. So I have a blue quadrilateral. There it is. I claim this is a cyclic quadrilateral. So what are the opposite angles of this quadrilateral? So if we look at angle, this is AHB, and angle AOB, this is cyclic quadrilateral. So this is a cyclic quadrilateral. What was our strange condition a moment ago for a cyclic quadrilateral? If we look at proposition 4, this is what I had started with. In proposition 4, you have a quadrilateral AHBO, and if the angles HAB and BOH are right angles, then it's cyclic. So HAB and BOH. HAB is a right angle. BOH is a right angle. So this is cyclic. By proposition 4. In a cyclic quadrilateral, the opposite angles add up to two right angles. Angle AHB and angle AOB add up to two right angles because they're opposite angles in a cyclic quadrilateral. Now, AHB is this angle. If you look at the angles around the center, the incenter, this angle alpha and this angle alpha are equal, or these are the same angle, call it alpha, because these triangles are congruent. This angle beta and this angle beta are equal because these triangles are congruent. And these angles, call them gamma, are equal because these triangles are congruent. So if I add up all of these angles, 2 alpha plus 2 beta plus 2 gamma, that's a whole angle that adds up to 2 right angles. Sorry, adds up to 4 right angles. Go all the way around. So alpha plus beta plus gamma, if you divide by 2, adds up to 2 right angles. But beta plus gamma is angle AOB. Angle AOB is beta plus gamma. And so alpha plus angle AOB is alpha plus beta plus gamma, which is 2 right angles. Which is also equal to angle AHB plus angle AOB. That's what we had proved over here. So if you cancel the angles AOB, we get alpha, the angle alpha, equals the angle AHB. And this turns out to be a very important fact. Angle AHB is this angle, and angle alpha is that angle. And these angles are the same. Okay, well, now there's just a lot of work to do, which I'll go through it step by step. Because it's worthwhile knowing that these really are correct proofs. But you don't have to worry that I'm going to ask you to prove any of this on a midterm exam, because I'm not. It's really too technical for an exam. But it's just interesting to see how much geometry goes into this proof of Heron's formula. So we got to this point, which turns out to be significant, that the angle alpha equals the angle AHB. So if you look at triangle COF, that's this little triangle. It's a right triangle with an angle alpha. If you look at triangle BHA, this is also a right triangle with an angle alpha. So triangle COF, this little triangle, is similar to triangle BHA. This big triangle and this little triangle, they're different in size, but they have the same angles, right? Right angle, angle alpha. If two angles of a triangle are equal to corresponding angles in a third triangle, in another triangle, the third angles have to be equal. So even though these triangles that I outlined with pencil are different in size, they're similar. They have the same angles. Okay. So similar triangles have sides that are proportional. So the ratio of the side AB to AH. This is AB. It's the side of the triangle opposite alpha. So the side of this triangle opposite alpha is CF. So AB is to AH as CF is to, see, what was AH? AH is the side next to alpha. The side next to alpha is OF. And CF is the same as CE is the same as AG. And OF is the radius of the inscribed circle. So another way of saying that is that the ratio of AB, the length of AB to the length of AG, is the same as the ratio of the length of AH to R. So this gets a star because we're going to come back to it. We're going to work out two more ratios from the fact that triangles are similar. So the triangle KAH is similar to triangle KDO. This is the point K, where this line crosses the line from O to H crosses the AB line. KAH, that's this triangle. KDO is this triangle. These angles are vertical angles, so they're equal. So this right triangle is similar to this right triangle. So this means that the ratio of A to H, that length, to the length of A to K, so AH to AK is the long side to the short side of this right triangle, will be the same as the ratio of the long side to the short side of this little triangle, OD over KD. And OD, again, is R over KD. So if you rewrite this, you get the ratio of the length of AH to R is the ratio of AK to KD. And here I have AH over R, and here I have AH over R. So the ratio of AK to KD is the same as the ratio of AB to AG. And this relation gets 2 stars. That's we're going to use it. So I have, this is one identity we need, and this is a second identity that we need. And there's going to be one more of these curious identities, which is, let's continue to look at this big picture. I have triangle BOK, BOK, which is a right triangle. And the altitude is OD, which is R. And triangle KDO is similar to triangle ODB, because if you take a right triangle, drop a perpendicular from the right angle to the hypotenuse, it divides the triangle up into 2 similar triangles. So this triangle and this triangle are similar. So triangle KDO is similar to triangle ODB. So this triangle and this triangle are similar, so the ratio of their sides are equal. So KD over OD, which is KD over R, plus OD is the radius of the inscribed circle. KD over OD is the short side to the long side of the right triangle. So that's the same as OD to DB. This equals OD to DB, but again, OD is equal to R over DB. So that says that the distance from K to D times the distance from B to D is equal to R squared. And that gets 3 stars. That's our third starred relation. So KD times BD, the product of those 2 lengths is R squared. We had this relation. AK over KD is AB over AG. So let me just write that down again. I mean, really, in a proof like this, all you can do is try to follow it line by line and appreciate how much work must have gone into trying to figure out an argument like this. So the ratio of AK to KD is the same as the ratio of AB to AG. And and you can add equals to equals, so add 1 to both sides. So this means that AB plus AG is to AG as AK plus KD is to KD. AB plus AG is the length from B to G. So this says the ratio of the length BG to AG and AK plus KD is the distance from A to D. This is the distance from A to D over the distance from K to D. So you can always multiply by 1 the distance from B to G divided by the distance from B to G is 1, and also the distance from B to D divided by itself is 1. So we have this sort of trivial identity. So if I take this and multiply top and bottom by BG, I get BG squared over AG BG. If I multiply this top and bottom by BD, I get AD times BD over KD times BD. But KD times BD is R squared. So this is BG squared over AG BG. This is AD times BD over R squared. So what we have is, if we cross multiply R squared, the distance from B to G squared, equals the distance from A to G, distance from B to G, times the distance from A to D, times the distance from B to D. BG distance from B to G is S. So this is the same as saying R squared S squared equals AG was S minus C, BG sorry, this is AG, BG, AD, BD. So AG is S minus C. AD is S minus A. BD is S minus B, and BG is S. So believe it or not, we have R squared S squared is S, S minus A, S minus B, S minus C. So RS is the square root of S times S minus A times S minus B times S minus C. And RS is equal to K. End of proof. Okay. Well, wasn't sure I could get it all done in an hour or so, but did. Again, this is really just to show you what I think is some very beautiful mathematics that uses, but it's not easy. And you have to somehow admire the ability of mathematicians a very long time ago to come up with a proof like this. Okay. So that certainly is all I'm going to do today. There's a nice discussion of the post history of Heron's formula in the epilogue to this chapter, which I would encourage you to take a look at. So if you want, you might say that the exam covers all of chapters 1, 2, 3, and 4, and everything in chapter 5. You have to know Heron's formula, but I'm not going to ask you to prove it or any part of it. There's enough geometry that we've done before this that is more than enough to try to understand. On Wednesday, I think I'll start with a kind of review for the exam and answer any questions you might have. I also remind you, we have problem sessions Tuesday, Thursday at 7. I'll also make one Wednesday at 7, Tuesday, Wednesday, Thursday at 7, and Friday in the afternoon at 4:30 in preparation for the midterm next Monday. Okay. Any questions before we stop for the day?
Professor,
Yeah.
question,
Go
oh,
ahead.
sorry. I was going to ask if there will be a review sheet prior to Wednesday so we could better prepare ourselves with
Well, the
questions.
review sheet is really the homework. The
Okay,
homework,
got it.
plus you really have to know, except for the Heron's formula, you have to know, because I'm going to ask you some of them, the grade theorems in each of the chapters and their proofs.
Okay, thank you.
Okay. And
Yes, I'm sorry. Can I see the last page again
sure.
of
Oops. Page 6. Well, the last page was just this.
yeah, that let me see, can you move it down a little?
Well, that's it. Yeah.
Yeah, yes, there we go.
Yeah.
Okay. Thank you.
But again, this is
Square root.
exactly in the text on page 126. Okay. Anything else? Looks like a beautiful day. Hope everyone gets to enjoy it a little bit. Okay. Be well. Bye-bye.
See you later, Professor. Have a good day.
Thank you.
Well,